The key idea of the paper is to present a generic framework for activation functions for neural fields, or also known as coordinate networks.
Welcome to Talking Papers, a podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher and knowledge disseminator. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today, we will be talking about the paper Beyond Periodicity, towards a unified framework for activations in coordinate MLPs, published at ECCV 2022 as an oral presentation. I'm happy to host the first author of the paper, Sameera Ramasinghe. Hello and welcome to the podcast. Can you introduce yourself?
I'm currently working as an applied scientist at Amazon, and I did my PhD from the Australian National University in 2020. And then I joined as a postdoc at AIML.
And who are the co-authors of the paper?
The other co-author of the paper is Professor Simon Lucey, who is the director of AIML.
All right, so let's get started. So in a TLDR kind of format, 2-3 sentences, what is this paper about?
So this paper is about proposing a new class of activation functions for coordinate MLPs. So as everyone knows, coordinate MLPs have a huge amount of applications in today's computer vision, such as nerve, image synthesis, and robotics, etc. So we propose a general theory for activation functions in these coordinate MLPs, such that they are allowed to encode high-frequency content without positional encodings, which is the generic way of doing it.
Excellent. Sounds super interesting. Okay. New activation functions are always exciting. Everybody wants to get their networks to work properly. So, but before we dive into the details, let's do a little bit of introduction. So what problem is this paper addressing?
The main problem is although coordinate networks are becoming super popular across many tasks, the problem with coordinate networks is that how do we let a network learn high frequency content? So the most popular way of doing this is to have a positional encoding layer. This is just a series of cosine and sine functions that you employ just before the coordinate network. So it just projects your low dimensional coordinates to high dimensional space, and it allows your network to learn high frequency content. But these positional encoding layers have so many drawbacks, like they don't behave well with respect to the first order gradients. So if you are just using your network as a kind of a middle component of some pipeline, and if you want your gradients to backpropagate all the way through the network, this positional encodings kind of messes up these gradients, and it's not really good for representing natural signals. So I always think of these things as hacks, the positional encodings. This is my personal opinion. I always think of positional encodings as a hack of letting a network learn high frequency content. So the paper was about, can we get rid of positional encodings and come up with well-designed activation functions such that they preserve these higher order gradients much more naturally and much more less noisy way, and still allow your coordinate network to learn high frequency content. So that's the idea of the paper, and that's what we do in the paper.
Okay, but let's take one step back for a minute, okay? So for those listeners that are not as brushed up on their NERF and what are coordinate networks, let's first talk about that, okay? So what is a coordinate network? What does it do? What's the input? What's the output? Let's choose, the simplest example, right? You have an image, right?
Yes.
You want to kind of encode an image as a network. So how does that work?
The thing is, I always think of coordinate networks as a way of representing data or signals. So traditionally, we've had different ways of representing signals, right? Most popular one is an image. So image is just a grid-based representation. You have a grid of pixels, right? And the way of representing these signals has a huge impact on the model or the network that's operating on them. For example, CNN. Let's take CNNs, right? So the reason that CNNs work so well is because of that grid structure of the image. So you have this convolutional kernel going all the way across it. But why are So coordinate networks are an alternative way of representing signals. For example, let's say we have an image, right? So the input to the coordinate network is xy coordinates, and the output is the pixel at this corresponding xy location. So for example, you can query each xy position and get the corresponding pixel RGB value out of it. So in a way, your network kind of becomes the signal. So the network weights of your network kind of encodes the signal. So why should people care about representing signals as neural networks? There are many reasons. The primary reason that I see is the compressibility. So for example, let's say you can encode a 3D scene, a complete 3D scene that maybe usually takes around like 1 GB of capacity if you try to do this in like a very grid-based or mesh-based representation, with a mesh-based representation. But with a coordinate network with few megabytes, you can represent this whole scene. So you can just input XYZ coordinates, and you can either encode the mesh or the occupancy or the sign distance functions, or you can encode the light field, density fields, anything. So that's the primary reason. The other reason that I think is most important is the continuity. So natural signals are naturally continuous, right? So that's why these grid-based representations are not ideal, because they are kind of discrete. They are a discrete way of representing a signal. But with a neural network, it's naturally continuous, and you can query up to extreme resolutions to get your outputs. So it's almost like infinite resolution data modality, these coordinate networks. And they also provide a natural architectural bias, which is Lifshitz smoothness. So because neural networks are naturally Lifshitz smooth, and natural signals are also Lifshitz smooth. So you have this all similarities between natural signals and coordinate networks. And that's why I think they are becoming so popular and starting to have so much applications around so much tasks.
Okay, let me just summarize everything that you just said. Right. So coordinate networks encode signals in a kind of a parametric way. They like bake that into a network. So for example, for a signal is an image. You take an image, every pixel in that image, you take the XY coordinate, you feed that into the network, you get the RGB value of that pixel, right? And then you encode the image, it's continuous, and it has a lot of benefits. All right, but what are like the main challenges then? So you said something about your method, right? That it enables, like, you can throw away the hack of positional encoding.
Yes.
So basically, what is the main challenge then that the positional encoding is solving, that you can throw it away, that your method is now solving?
Yes. So I'll take a step back. Let's put the positional encodings away for a little bit. So why can't we just use a neural network to, let's say, a ReLU network, a sigmoid network, or use traditional activation functions for this? So the problem is that there's something called spectral bias of neural networks. The problem with these traditional activations is these networks take exponentially more time to learn high frequencies. But the problem with natural signals is like they have high frequencies. Let's take an image. So they have like these subtle variations and lots of high frequencies. So if you just employ a neural network with traditional activation functions to learn this signal, what happens is it will learn these low frequencies very quickly, but the high frequencies, no matter if you train for days, it still cannot learn this high frequency. So it's not a great way of learning natural signals. Having a positional encoding layer, it kind of allows the network to increase its bandwidth and encode these high frequencies. But moving forward, so if we actually analyze positional encodings, the problem is like positional encodings are used in conjunction with ReLU networks usually. And ReLU networks are piecewise linear. And because of this piecewise linearity, you can't get high order gradients with ReLUs. And that's why I called it a hack. I call it a hack because like ReLU networks are not ideal, and positional encodings just allow them to learn signals that look good. There's this really important paper called Siren is the short name for it. So it came into 2020. Siren paper showed that you can actually get rid of positional encodings and have sinusoidal activations employed in your coordinate network and get really good reconstruction, as well as really good first order and high order derivatives. I think this is a really good paper because it showed that there's a way of getting rid of these drawbacks associated with positional encodings, which is not preserving this gradient information properly. But the problem still remained, because like the thing that motivated us most was what was making this siren or sinusoidal activations work so well. So that was a question mark, because is it the periodicity? Is it the derivatability? Is it the Lifshitz smoothness? What's it? So what we did was like take a step back and investigate, is periodicity important, or are there more fundamental forces at play here that allow an activation function to encode high frequency details simultaneously, encode or preserve this high frequency, high order derivatives or first order high order derivatives. So what we discovered was that no, periodicity is not that important. There are more fundamental forces, which are rank and the Lifshitz smoothness. I'll explain a little bit more about that.
Before we dive into your method and what you guys did, so if you have to name 3 papers that anyone that wants to read your paper and understand it well should read, which papers would those be?
I think the first and foremost, most important paper is the paper by Sameera Ramasinghe. It's called On the Spectral Bias of ReLU Networks. It actually shows the problem associated with neural networks, why they can't learn high frequencies without these special activation functions or positional embeddings. So it's kind of a more fundamental theoretical paper. That's a really nice one. So the second paper I think would be most important would be a NeurIFS 2020 paper by Matthew Tansik. It's called Fourier Features Let Networks Learn High Frequencies. So it actually shows that having a positional embedding layer allows your ReLU network to increase its bandwidth and learn more high frequencies very quickly. And third and most relevant paper, I'd say, to our work is the Siren paper, which came in 2020, also NeurIFS paper by Vincent Sitzman. So it showed that you can actually get rid of positional embeddings and have these sinusoidal activations that simultaneously preserve better derivatives and also learn high frequency details. So I think those 3 are the most important papers that are relevant to our paper.
Okay, so now let's dive into the approach. So what did you do and how did you do it?
Yeah, like I said, the problem we were trying to address is to how to get rid of positional encodings, because I think of these positional encodings as kind of a hacky way of doing things. Because like positional encodings are normally used with these ReLU activation functions, and ReLUs are piecewise linear, and they have like really messy, they don't actually have high order derivatives even. And if you just use them with positional encodings, they end up giving you like really messy first order and high order derivatives. And it's not like really a natural way of representing a continuous natural signal. So Siren paper showed that we can have activation functions that allow you to get rid of positional encodings. But a problem associated with sinusoidal activations is that it required a very specific initialization scheme. And even if you use this specialized initialized scheme, one problem was that it's quite unstable. I mean, if you try to use it in a complex setting such as neural radiance fields or some geometric application, it tends to get out of these good locations in the parameter space and move to like really noisy places. So it's quite unstable in terms of convergence. So what we wanted to investigate was to take a step back and see what's really special about these sinusoidal activations. Is it the periodicity, or is it something else? So what we discovered was that there are more fundamental forces at play here. Like the 2 main forces that we discovered were the rank and the Lifshitz smoothness of the learned representation of the hidden layers. So if you have some activation functions such that they are equipped with these fully connected networks, so they are employed on top of these fully connected networks, and then you get the representation out of these layers. And if you just measure the rank and the Lifshitz smoothness of these embeddings that you get out of these layers, there's a trade-off between them. So if you have a higher rank, that means you can memorize the points very well. But that's only one part of the story, right? Because you have to generalize as well. For example, if you have sparse samples, you don't want to just memorize the point. You want to smoothly interpolate between them. So you also need the Lifshitz smoothness. So there's this push and pull between these fundamental forces. Because if you have like a really high lift shift constant, then your ability to memorize the points go down a little bit. And if you just increase the rank a lot, you can memorize the points very precisely, but your lift shift smoothness goes down. So are there the problem that we addressed was, are there any activation functions that allow us to kind of control the trade-off between these two and hit that sweet spot such that you can memorize the points? That means you can encode really high frequency details and also smoothly interpolate. So we discovered that there's a whole class of activation functions, and there are fundamental rules associated with this class of activation functions. For example, some of them are just Gaussians, Laplacians, exponential signs, and quadratic functions, multi-quadratic functions. All of these functions actually preserve these properties that we need to preserve in order for these activation functions to encode high frequency details. So that's actually the main contribution of the paper.
Right. So let me summarize very quickly. And I think this is like the most interesting part of the work, is that you found that basically if there's this trade-off between smoothness and, let's call it, the high frequency or reconstruction quality or overfit to the data points that you have. And the things that actually control that are the rank versus the Lipschitz constant, right?
Absolutely.
So, and if you find a good function that knows how to kind of balance that, then you get the best of both worlds.
Yes.
And from my side, I had some work on surface reconstruction using sine distance functions that are learned from a network. And that's exactly what we found. We found that, as you said, sirens have those high frequencies. They give good reconstructions. But if you move a little bit, you get this type of, we called it ghost geometries. You get this noise everywhere that you can't get rid of. And the initialization is so important. If you did something a little bit off, then that's it. It's not going to work well.
Yes.
And these functions that you're proposing are exactly to solve this problem.
Yes.
But my current question is, well, how do you know which one to choose?
Yeah, that's the problem. And also the thing is, like, we propose a general set of rules for this activation functions. So the thing is, if you have an activation functions that fulfill these properties, it basically boils down to the rank and smoothness again. So if you have some activation functions, one critical thing that I forgot to mention is that we connect these properties, this rank and Lipschitz constant, to the first order derivatives and the second order derivatives of the activation function. That's actually the second contribution of the paper. We don't come out and just say that as long as an activation function preserves these two properties, it's good. We also connect that to the first order and second order derivatives of the activation functions, which kind of gives you a more tangible way of choosing activation functions. So if you can actually control the first order derivatives, and also if your second order derivatives are bounded, magnitude of your second order derivatives are bounded, and if you have some hyperparameter that you can control these two properties, then it's a suitable activation function. For example, take a Gaussian, right? So if you just change the variance of the Gaussian, you can control the first order derivatives and the second order derivatives within some bound. So that gives you a good activation function that you can control these two properties. So that's actually a very high level overview of the criteria that you need to in order to choose these activation functions. The thing is, like, we showed that these activation functions kind of can be used for any application that you need to employ coordinate networks on. For example, neural radiance field, image reconstruction task, audio reconstruction tasks. So the basic thing is, like, if you have been using positional encoding so far with ReLU networks, I would just like to pull you towards our work and advertise that, just replace that with a Gaussian network or an activation function that we propose, an alternative one, and see what happens. Like, it's very stable and it's very robust to different initialization schemes. And in our paper, we showed this whole set of experiments with this. How much does this change in these hyperparameters?
Yeah. So, right, you made some interesting claims, right? That these new functions they provide this balancing effect between the smoothness and the reconstruction ability. And well, you needed to validate that, to make that point. So, what experiments did you do?
Yeah, so a good chunk of our paper is dedicated to the theory, and by experiments we actually needed to like verify our theoretical claims and hypotheses. So what we did was like take these activation functions and showed that it can be employed across a whole range of empirical tasks like neural radiance fields, image reconstructions, and audio reconstruction and stuff. And the second thing we did was like to verify our claims about this rank and the Lifshitz constant. So we showed that by controlling these hyperparameters, you can just move from one extreme to the other extreme, such that you have like really high smoothness and poor reconstructibility. And on the other extreme, you have very good reconstruction capacity, but poor generalization. So we also kind of, in the theory, we connected this to the eigenvalue spectrum of the hidden layers. So for example, here's an interesting thing. It's not really straightforward to calculate the Lifshitz constant of a neural network. It's an NP-hard problem, but we provide a really good empirical way of calculating this by providing based on the eigenvalues of the single values of the hidden representation. And we showed that our theoretical claims exactly match the empirical findings that we show in the paper. So those three are, I'd say, the most important aspects that we touched in the experiment section. But like I said, it's kind of a more theory biased paper, but experiments were dedicated to like more solidifying these theoretical claims.
Yeah. So usually in these type of episodes, I ask, well, when does your method fail? But because this is a theoretical find, then I'm not sure that it does fail. Like, does it? So have you experienced anything that was, let's say, odd or abnormal or didn't completely work as you expected?
Yeah. I wouldn't say this is exactly a fail case, but I would say this is kind of a drawback, room for some future improvement, because this is actually a common problem associated with positional encoding, sirens, or any kind of coordinate network that you can get your hands on. The problem is that how to optimally design hyperparameters. For example, in siren, if you have like a sine with lots of high frequencies, you get like very bad reconstructions. You have to optimally design it, get the hyperparameters right. Even with positional encodings, how much frequencies should I have in the positional encoding? That affects your reconstruction quality. And with the new class of activation functions that we propose, the same problem persists. Like, what are the optimal hyperparameters? So I think the next big question for coordinate networks is, can we design the ideal coordinate network given some data, such that we have the perfect reconstruction and we can have the perfect smooth generalization? Right now, it's like all trial and error. So I guess the next broader question is, because in a natural signal, we have different spectral properties. For example, if you take an image, you have in some location, you have high frequency variations, and in some locations, you have low frequency variations. And ideally, your neural network should also have this locally varying hyperparameters, I would say. For example, let's take a Gaussian activated neural network. This sigma, can we actually change it locally such that you get really good reconstruction all the way through? Let's take a nerve, and in the nerve you get like really high frequency details, and in places that you have like really sparse sampling, can you also interpolate in those locations, learning from some priors that you learn from other places?
Right. So basically what you're saying is, at the moment, the parameters of those activation functions, you kind of have to tweak it, right? You have to fine tune it to find the right set of parameters for the specific test that you're trying to solve, right? If it's
yes.
A nerve or image reconstruction or surface reconstruction or whatever. And it would be interesting to find a way to have those parameters kind of trained as well. And not only trained, but local, have like a different
analytically designed. Yeah.
Absolutely. Super interesting. I think it's super interesting, and actually, like, all of this work ties a lot into several episodes we had in the podcast. So there's the Lifshitz MLP paper that was in SIGGRAPH. There was the Bacon paper. There's our Diggs paper. All of those papers kind of try to, they mostly focus on surface reconstruction using like training a neural network to learn a sine distance function to reconstruct the surface. And our Diggs was kind of trying to, minimize the second derivative almost everywhere, except in certain places where it should be really, really high. And this one kind of like is like an umbrella paper that takes all of those and says, well, here's the theoretical background to that. and here's the trade-off, and you can select whichever activation function that you want. Now, one question that I found interesting in the paper, and I wasn't sure what the answer was. So you basically say, well, we can manage without the positional encodings, right? Because our new activation functions can play that role of bringing those high frequencies in. But in practice, when you use the positional encodings, you get better results. Do you have any kind of intuition as to why that is?
Well, I guess like better results in terms of, I guess it's comparable. So we show that we get like comparable results. That's why I kind of want to emphasize this. I'm not, so our paper is not actually saying that using these activation functions will give you like 1% increase. I'm saying that as long as you tune these hyperparameters correctly, even Siren, Gaussian, so positional encodings, they will give you like really nice looking reconstruction. But here's the caveat. If you analyze your first order gradients in the positional encodings, they are really bad. And Siren is very sensitive to the initialization, unstable. But our activation functions actually can give you the best of the both worlds, and it can give you good reconstructions, comparable. It's not PSNR wise, it might not be better. But if you compare the PSNRs of the first order and second order derivative maps, it's way, way better than positional encodings. And it's very robust to different initialization schemes and in different settings compared to Siren.
Yeah, so that's actually very interesting. All of these coordinate networks, basically, they can converge into multiple good solutions, right? And when I say good, it means they look good, right? You get the bold numbers. But yes, what you're saying is, well, while those solutions are visually good, if you kind of move a little bit around that area, because everything is so noisy on the second and first order derivatives, then it's going to be messed up eventually. And
yes,
if you use your suggested family of activation functions, you're saying, well, the reconstruction is going to look just about as good. But now if you move around these areas, it's still going to stay good because now it's a good solution. It's not like a noisy, small area of that solution. It's actually the good solution that you wanted.
That's one key advantage. The other advantage is like these first order gradients are super important if you want your gradients to propagate through the network to some layer before that. For a good example of this is, let's say we are given like a neural radiance field setting without camera poses, and let's say we want to update the poses as well. So the poses actually come in a layer before the neural network. So you want to backpropagate through the network to these poses and update the poses. And if you have positional encodings, it's going to really mess up these updates. It's not going to converge at all because these gradients are noisy. There's a paper called Bundle Adjusted Radiance Fields, BAF, in ICCV 2021, which showed this. So they had to do all these tricks like adding, starting with a low number of frequencies in the positional encoding layer and gradually adding more frequencies to it. So it's like a very cumbersome way of training it. But if you use something like Gaussian activations, you can just get rid of all these cumbersome, these heavy training mechanisms. You can just backpropagate all the way through to the poses and update them. And I'm just saying this as an example. There could be like humongous amounts of applications that you need to actually backpropagate through your network, right? And our activation functions provide an ideal platform to that compared to positional encodings.
Okay, so let's move on to the conclusions and future work section. So how do you see the impact of the paper going forward? And are there any interesting papers that follow this one?
Yeah. So they have been, people have been trying to replace their coordinate networks with our activation functions. So there are, I think, around 5-6 citations for the paper for now. So, but I'm actually communicating a lot with people from well-known groups over email about these activation functions, and they're trying to employ these activation functions in their work. So I hope they would become successful, and I'm pretty sure they will. So in terms of future works, the next big thing I'm looking at is, so this is quite an interesting thing. I want to pitch this. The way I see it, there's this inherent trade-off. So for people who are familiar with NERF, you might know that NERF takes days to train. It's very slow. So the problem with neural networks is that when you are trying to train a coordinate network on a 3D scene, like with a large amount of data, it's very compressible. But the downside of that is like it takes way longer training times. It's so much slow to train. But that's why people have reverted to like these grid-based representations for neural radiance fields. For I'm taking an example, neural radiance fields as an example because that's a popular example. People have these planoxels, tensor radiance fields, and instance NGP by NVIDIA. All of these are just grid-based representation. They are extremely fast, but the problem is memory-wise, they are very expensive. So there's this trade-off. Neural networks, you have the compressibility, but it's slow. But grid-based representation, volumetric representations, fast but memory intensive. So this is inherent trade-off. But can we break this? I think it's not my personal opinion. It's the opinion of my lab at AIML. So we think that coordinate networks need special treatment, and they can enjoy special optimization procedures such as second order optimizers, because they are infinitely derivatable. These activation functions are infinitely derivatable, so they have like very well defined Hessians. So, and they are shallow. They are not like 10 layer, 12 layer deep networks, like 4-5 layers deep. So we can write analytical Hessians, analytical second order derivatives, and can we come up with like an extremely fast optimization technique that can give you best of the both worlds, instant training and compressibility. I think that's would be a game changer if we can come up with that.
All right. So moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments that you had in the review process that made the paper better.
Yeah, I mean, I think most of the reviews were like very positive, and they were kind of very constructive and supportive. One key comment was exactly something that I mentioned earlier, like the tuning of the hyperparameters. So the one review was like really concerned about the tuning of hyperparameters, but we kind of explained in the rebuttal that it's a common problem associated with any coordinate network up to now, and it's a future work that we should look into.
Yeah. Okay, excellent. Thank you very much for being a part of the podcast, and until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.